Close your eyes and try to imagine a number so vast it breaks your brain. 13,800,000,000 years. That's how long ago the universe began, though some round it to 15 billion for simplicity. But what does that really mean? What was the Big Bang? Here's what most people get wrong. They imagine empty space, a dark void, and then suddenly, boom, an explosion happens somewhere in that darkness. But that's not what occurred. There was no darkness. There was no void. There was no somewhere for an explosion to happen. Before the Big Bang, there wasn't even a before, because time itself didn't exist yet. The Big Bang wasn't an explosion that happened in space. It was an explosion of space itself. Every point in the universe, every location you can think of, was compressed into something unimaginably small and dense. Not just the matter, but space itself, the very fabric of reality, was scrunched down smaller than the tiniest atom you can imagine. And inside this impossible speck existed all the energy and all the potential for everything that would ever exist. Then it began expanding, not into anything, because there was no anything to expand into. Space itself was growing, stretching, creating new distance between points. And as it expanded, conditions changed dramatically. The temperature in those first moments reached levels we can barely express with numbers, quadrillions upon quadrillions of degrees. This wasn't just hot enough to melt steel or vaporize rock. This was so hot that atoms couldn't exist. Even the particles that make up atoms couldn't hold together. What's truly staggering is the timeline. In less than 1 second, in a fraction of time so small it would take a page full of zeros after the decimal point to write it down, the entire structure of our universe was established. The fundamental forces that govern everything separated from each other. The basic particles that would eventually build galaxies, stars, planets, and people came into existence. The laws of physics that we use to understand our world today were written into the fabric of reality. Scientists didn't just dream this up. We have evidence. When astronomers point telescopes at the most distant galaxies, they're looking backward in time because light takes so long to travel across space. The farther away something is, the longer its light has been traveling to reach us, which means we see it as it was in the ancient past. And what they've discovered is remarkable. The farther back they look, the younger and simpler the universe appears. Galaxies closer to the beginning of time are smaller, more chaotic, filled with younger stars. But the most compelling evidence comes from something you can't see with your eyes. In every direction we look, space itself is filled with a faint microwave radiation heat left over from when the universe was just 380 years old. It's like finding warm ashes in a fireplace and knowing there was once a roaring fire. This cosmic microwave background is the afterglow of creation, cooled and stretched by billions of years of expansion, but still detectable with the right instruments. That moment 8 billion years ago wasn't just the beginning of matter or energy. It was the beginning of everything space, time, cause and effect, the very possibility of existence itself. Picture a gunshot frozen in time. The trigger has been pulled, the powder has ignited, but the bullet hasn't moved yet. Now compress that entire moment, the explosion, the force, the energy, into a space billions of times smaller than the period at the end of this sentence. That's roughly where our universe began, and what happened next occurred faster than thought itself. In the first trillionth of a trillionth of a trillionth of a second after the Big Bang, the universe underwent the most dramatic transformation in its entire history. Everything that would ever exist, all the matter in all the galaxies, all the energy that would ever flow, Every particle that would ever form came rushing into being from that impossibly dense starting point, but we're not talking about things appearing in space. Space itself was being created in that same instant, along with time. Think about what that means. There was no clock ticking. There was nowhere for things to happen. The very concepts of location and duration were being born alongside everything else. The universe wasn't expanding into some pre-existing emptiness. It was creating the emptiness as it went, stretching out the fabric of reality itself like an inflating balloon, except there was no outside to the balloon. In those first inconceivable fractions of a second, pure energy dominated everything. The temperature soared to levels that make the core of our sun look like a frozen tundra by comparison. We're talking about conditions so extreme that the four fundamental forces we know today, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single force. They hadn't separated into their distinct identities yet. Then, as the universe expanded, it cooled. When we say cooled, we still mean temperatures of trillions of degrees, but physics cares about relative changes. As the temperature dropped, those fundamental forces split apart from each other, each taking on its unique characteristics. First gravity separated, then the strong nuclear force, then the electromagnetic and weak forces divided. This wasn't arbitrary. The specific sequence and timing of these separations determined what kind of universe we'd end up with. Within that first second, quarks appeared, the building blocks of protons and neutrons. They didn't drift lazily into existence. They materialized from pure energy in a process that sounds like magic but follows strict mathematical laws. These quarks immediately began combining, forming the first protons and neutrons, while the universe was still unimaginably hot and dense. What makes this even more remarkable is that scientists have actually managed to piece together this timeline. Using particle accelerators, they've recreated conditions similar to those first moments, smashing particles together at incredible energies to see what emerges. Using mathematics and observations of the cosmos today, they've worked backward, running the clock in reverse to understand what those opening moments must have been like. Everything you see around you, the chair you're sitting on, the device you're reading this on, your own body, is made from matter that crystallized into existence in that first second. The atoms won't form for hundreds of thousands of years yet, but their fundamental components, the quarks and electrons that will eventually build them, all appeared in that brief, violent, creative instant when the universe was less than 1 second old. Imagine trying to photograph a newborn baby, but you have to wait 380,000 years after birth to take the picture. That's essentially what the cosmic microwave background represents. The oldest photograph of the universe we can possibly take, captured not with a camera, but with radio telescopes pointed at the sky. For the first 380,000 years of its existence, the universe was completely opaque. You couldn't have seen anything even if you'd been there with the most powerful eyes imaginable. The entire cosmos was filled with a searingly hot plasma, a thick soup of electrons, protons, and photons all jumbled together. Light couldn't travel in straight lines because it kept bouncing off free electrons, absorbed and re-emitted over and over again, trapped in an endless pinball game. Think of it like trying to see through a thick fog. The fog isn't a solid wall, but light can't penetrate very far because water droplets keep scattering it. The early universe was like that, except instead of water droplets, free electrons were doing the scattering. Every photon of light would travel a tiny distance, hit an electron, get absorbed, then re-emitted in a random direction. The universe glowed with incredible brightness, but nothing could be seen clearly through this cosmic haze. Then something pivotal happened. As the universe continued expanding and cooling, it reached a critical temperature about 3.0 degrees Kelvin, roughly half the temperature of the Sun's surface. At this temperature, electrons finally slowed down enough to be captured by atomic nuclei. Hydrogen atoms formed. Helium atoms formed. Suddenly, the free electrons that had been scattering light were locked up inside atoms. The fog lifted. For the first time in cosmic history, light could travel freely through space. Photons that had been trapped, bouncing around endlessly, were suddenly released. They began streaming through the universe in straight lines, carrying with them a snapshot of what the cosmos looked like at that precise moment. This event is called recombination, and it marks the moment the universe became transparent. Those photons have been traveling ever since. As the universe expanded over the following 13 billion years, space itself stretched, and those photons stretched along with it. Light that began as visible and infrared radiation has been pulled and elongated by the expansion of space. Its wavelength stretched until it became microwave radiation, the same kind of radiation your microwave oven uses to heat food, though much, much weaker. In 1964, two scientists named Arno Penzias and Robert Wilson were testing a sensitive radio antenna when they detected a persistent hiss coming from every direction in the sky. They initially thought it was interference, maybe from pigeon droppings on their equipment. But after cleaning everything and checking repeatedly, the signal remained. They'd accidentally discovered the cosmic microwave background, the cooled remnant of that ancient light from when the universe first became transparent. Today, we've mapped this radiation with exquisite precision using satellites. It's not perfectly uniform. There are tiny temperature variations, hot spots, and cold spots that differ by only a few millionths of a degree. These tiny ripples represent slight density differences in the infant universe, the seeds that would eventually grow into galaxies, galaxy clusters, and all the large-scale structure we see today. We're literally looking at baby pictures of creation itself. When the universe cooled to about 3.0 degrees, still hot enough to melt any metal you can name, something remarkable happened that would define the structure of all matter forever after. For nearly 380 years, electrons had been racing around freely, too energetic to settle down, too hot to be captured. But as the temperature dropped below that critical threshold, these electrons finally slowed down enough for atomic nuclei to grab hold of them. Picture a dance floor at closing time. During the height of the party, everyone's moving too fast, bouncing off each other, too energized to pair up. But as the music slows and the energy dies down, couples finally come together. That's what happened in the cooling universe. Protons, which had been formed in the first few minutes after the Big Bang, finally captured electrons and became hydrogen atoms, the simplest and most abundant element in the universe. It sounds simple, but this moment changed everything. Before this, the universe was ionized plasma, a state of matter where electrons roam free, separated from their nuclei. After this, the universe was filled with neutral atoms, with electrons bound in orbits around nuclei, creating stable structures that could persist and interact in entirely new ways. The process wasn't instantaneous across the whole universe, but it happened relatively quickly on cosmic timescales over about 100 years. Hydrogen atoms formed first, each one consisting of a single proton nucleus with a single electron orbiting it. Then helium atoms formed, with 2 protons and 2 neutrons in the nucleus, capturing 2 electrons. These 2 elements, hydrogen and helium, made up about 98% of all the matter in the universe. Tiny traces of lithium formed as well, but everything else, all the heavier elements, didn't exist yet in any significant amount. The ratio wasn't random. For every 12 hydrogen atoms that formed, there was roughly 1 helium atom. This 3:1 ratio by mass emerged directly from the conditions in the first few minutes after the Big Bang, when protons and neutrons combined in the intense heat to form the first helium nuclei. Scientists have measured this ratio throughout the universe, in the oldest stars and the most distant gas clouds, and it's remarkably consistent, powerful evidence that this story of the universe's first moments is correct. What makes this moment so significant is that these atoms, specifically hydrogen, were the raw material for everything that came after. Every star that would ever shine would form from collapsing clouds of hydrogen. Every galaxy would be built from it. The hydrogen atoms that formed in that ancient cooling period still exist today. Some of them are in your body right now, bonded with oxygen to make the water in your cells, incorporated billions of years ago into organic molecules. When astronomers look at the most distant objects in the universe, they're seeing light that passed through clouds of this primordial hydrogen. The light carries signatures, absorption lines that tell us about the atomic structure of matter in the early universe. And what they see confirms this picture: hydrogen and helium in that characteristic ratio, the chemical fingerprint of the universe's childhood. Those first atoms were democracy at the atomic level, simple, identical, spread relatively evenly through space. But they carried within them, in their slight clustering and in the pull of gravity, the seeds of all the complexity that would follow. For roughly 200 million years after the cosmic microwave background was released, the universe entered what astronomers call the Dark Ages. Not because anything sinister was happening, but because, quite literally, there was no light. The ancient glow from recombination had faded and stretched into invisibility. The first stars hadn't formed yet. If you could have floated through space during this era, you would have experienced absolute, complete darkness in every direction. A blackness so total it's hard for us to comprehend. But in that darkness, something was stirring. Gravity, the weakest of the fundamental forces, but the most patient and relentless, was at work. Remember those tiny density variations we can see in the cosmic microwave background, those slight differences where matter was just a fraction denser in some regions than others. Gravity amplified them. Where there was slightly more matter, gravity pulled even more matter in. Dense regions grew denser. Clouds of hydrogen and helium gas began to collapse inward on themselves. As these clouds contracted, something crucial happened. When you compress a gas, it heats up. The same principle that makes a bicycle pump warm when you use it. These collapsing clouds of primordial gas grew hotter and hotter at their cores. Pressure built. Atoms slammed into each other with increasing violence. For millions of years, this process continued, clouds collapsing under their own gravity, cores heating up, until finally, in the densest regions, conditions reached a critical threshold. The temperature hit 10 million degrees. At this point, hydrogen nuclei protons were moving so fast and colliding with such force that they overcame their natural repulsion and fused together. Nuclear fusion ignited. Hydrogen began converting into helium, releasing tremendous amounts of energy in the process. A star was born, then another, then billions more. The cosmic dark ages ended, and the universe blazed with light for the second time in its history. These first stars were nothing like our Sun. They were monsters, some containing hundreds of times more mass than our Sun, burning thousands of times brighter, with surface temperatures reaching 100 degrees. They were composed almost entirely of hydrogen and helium because nothing else existed yet in significant quantities. No carbon, no oxygen, no iron, just the simplest elements forged in the Big Bang's first few minutes. But these massive stars lived fast and died young. While our sun will burn for about 10 billion years, these first-generation giants exhausted their fuel in just a few million years. And their deaths were spectacular. They exploded as supernovas, blasts so powerful they briefly outshone entire galaxies. In those final explosive moments, in the incredible heat and pressure of a collapsing stellar core, something miraculous happened. Heavier elements were created. Carbon formed, oxygen formed, silicon, iron, gold, uranium elements all the way up the periodic table were forged in those dying stars and their supernova explosions. When these stars detonated, they scattered these newly created elements into space, enriching the cosmic gas clouds. The next generation of stars would form from this chemically enriched material. They would be different, smaller, longer-lived, and capable of forming rocky planets. Gravity had sculpted the first stars from nearly uniform gas, and in doing so, transformed the universe from a simple place of hydrogen and helium into a cosmos with the chemical complexity necessary for planets, for life, for everything we know. Look at your hand right now. The carbon atoms in your skin, the calcium in your bones, the iron flowing through your blood. None of these existed when the universe began. The Big Bang only created the simplest elements, hydrogen, helium, and traces of lithium. Everything else, every element heavier than these primordial three, had to be manufactured somewhere else. That somewhere else was inside the nuclear furnaces of stars. When the first stars ignited and began fusing hydrogen into helium, they started a process of cosmic alchemy. In their cores, where temperatures reached tens of millions of degrees and pressures were immense, nuclear fusion didn't stop at helium. As stars aged and their cores grew hotter, helium nuclei fused together to create carbon. Carbon fused to make oxygen. Oxygen combined to produce neon, magnesium, silicon. The process continued up the periodic table, each step requiring higher temperatures and more extreme conditions. But there was a limit. Iron was the end of the line. Fusing iron actually consumes energy rather than releasing it, so stars couldn't forge anything heavier through normal fusion. For elements beyond iron, copper, silver, gold, uranium, something more dramatic was required. That something was the death of massive stars in supernova explosions. When a massive star exhausted its fuel, its core collapsed catastrophically, triggering a rebound explosion so violent that temperatures briefly exceeded those of the Big Bang itself. In those final seconds, in the shock wave tearing through the star, neutrons slammed into iron nuclei so rapidly they built up all the heaviest elements in the periodic table. Gold, platinum, lead all forged in stellar death throes. These explosions scattered the newly created elements into space, where they mixed with clouds of hydrogen and helium. New stars formed from this enriched material, and some of those stars had planets. On at least one of those planets, these stellar elements combined in ways that produced life. Every breath you take, every thought you think, happens because ancient stars died and released their treasure of heavy elements into the cosmos. Right now, as you read these words, the galaxy closest to ours, Andromeda, is racing toward us at about 110 kilometers per second. But nearly every other galaxy we can see is doing the opposite. They're rushing away from us, and the farther away they are, the faster they're receding. This isn't because we're at some special location in the universe, some cosmic center that everything is fleeing from. It's because space itself is expanding, carrying galaxies along with it like raisins in rising bread dough. This discovery ranks among the most profound in human history. In 1929, astronomer Edwin Hubble measured the light from distant galaxies and noticed something strange. Their light was shifted toward the red end of the spectrum redshifted, which meant they were moving away from us. More surprisingly, galaxies twice as far away were moving twice as fast. Galaxies 3 times as far were moving 3 times as fast. The relationship was precise and unavoidable. The universe was expanding. Think about what this means if you run the clock backward. If galaxies are moving apart now, they must have been closer together in the past. Go back far enough, and everything in the observable universe must have been compressed into an incredibly small, dense state. This was one of the first major pieces of evidence for the Big Bang theory. The universe had a beginning, and it's been expanding ever since. But here's where it gets even stranger. In the 1990s, astronomers were trying to measure exactly how much the expansion was slowing down. They assumed gravity would be gradually pulling everything back together, decelerating the expansion like friction, slowing a spinning top. They studied distant supernova explosions as cosmic measuring sticks, expecting to find the universe's expansion was gradually decreasing. Instead, they discovered the opposite. The expansion isn't slowing down, it's speeding up. Galaxies are accelerating away from each other. Something is pushing the universe apart, working against gravity, and this force is winning. Scientists call it dark energy, though that's really just a name for our ignorance. We don't know what it is. It doesn't emit light, doesn't interact with matter in any way we can detect directly, but it makes up about 68% of all the energy in the universe. This accelerating expansion has profound implications for the universe's future. Billions of years from now, distant galaxies will be racing away so fast that their light will never reach us. The observable universe will shrink. Eventually, only our local group of gravitationally bound galaxies will remain visible. The rest of the cosmos will have receded beyond a cosmic horizon, their light stretched to infinite wavelengths by the expanding space between us. For now, though, we live in a golden age for cosmology. We can still see the cosmic microwave background. We can observe distant galaxies as they were billions of years ago. We can trace the expansion back to its origin and forward into the far future. The universe that began in an impossibly small point continues its grand expansion, carrying us along on a journey that started 8 billion years ago and shows no signs of stopping, only accelerating into an ever larger, ever older, ever more distant future.